Hello there. So we are starting or we are continuing our section 1.1. So in the previous portion or video 1 of section 1.1, we saw or we learned a method to solve the system of equations, system of linear equations by using matrix. So we created an augmented matrix and we performed some operations, and we showed in that example that the operations we do on those equations, we had three equations and in three variables. So we can multiply an equation by a number and add it to another equation, or we can multiply a whole equation by some number, and or we can interchange some equations. So same operation we can do on matrix, and those are called, when we do those operations on matrices, we call them elementary row operations, because matrices have rows. So an equation is treated as a row of a matrix. So what are those operations in words? We see here. So the first one, we call it replacement. So in this operation, we can replace a row by the sum of itself. So by adding that row to a multiple of another row. So in other words, by adding a multiple of another row to our row which we want to change. And these operations have to go in a systematic order. We cannot just haphazardly do them, because then it could, if we do it haphazardly, then it could make something that we kind of created. For example, in a place we created a 0. If we do not follow the instructions and do not go in order, then we might end up creating a non-zero number at the place where we had created a 0. So then we have to go back and make it 0 again, and then redo the operation, so it can increase the amount of work. So if we go in a systematic manner, then everything will be fine. So we can add a multiple of one row to another row to change this later row. And when we do that, only this one row will change, not the one that we multiplied or the one that we used to change this row. The second one is called interchanging or interchange of two rows. So we can switch two rows. So for example, in place of row 1, I can move the third row, and then first row goes in the place of the third row. The scaling, or so what in this case we do is multiply all entries in a row by a non-zero constant. So sometimes we have to do that. For example, if often we would like some of the places we would want a 1 in there. So it could be that we have a 2 or a 5 or a -2 or -1. So we have to divide by the number so that it becomes 1. But you remember dividing a number. So for example, if I have a -2 and I want to divide it by -2, it is the same thing as saying -1/2 multiplied by -2. So instead of saying we are going to divide -2 by -2, we say we multiply -2 by -1/2. So that's what we mean by when we multiply a row by -1/2, or we multiply a row by 1/2 or 1/3 or 1/5 or 2/5, whatever. So that is scaling. Now we say that two matrices are row equivalent. Okay, so these matrices are row equivalent if there is a sequence of elementary row operations that transforms one matrix into the other. So if by applying some row operations that we just learned, the three operations, if we apply row operations on a matrix and it gives us a new matrix, now it could be one row operation, it could be two row operation, it could be a bunch of row operations. So wherever we stop, so all these matrices in between. So if we start with a matrix A and we apply row operation, and it changes to a new matrix, or it changes one row of the matrix. And then we apply another row operation, and then another row operation, and we keep doing, and we get like 9 matrices in between, for example. So from the first and the last, we have 9 matrices. Then all these matrices are row equivalent to each other. Now, it is important to note that these row operations are reversible. Now, if the augmented matrices of 2 linear systems are row equivalent, then the 2 systems have the same solution set. So, as we saw previously, if you recall, we called 2 systems of equations equivalent if they have the same solution. So here we are saying the 2 matrices are, or augmented matrices basically, and 2 matrices of 2 linear systems are row equivalent, then the 2 systems have the same solution set. 2 fundamental questions about a linear systems are as follows. Is the system consistent? In other words, we are asking, does at least one solution exist? Because remember, that's the definition of being consistent, that the system should have at least one or infinitely many solutions. We cannot have 2 solutions or 3 solutions. We can have either one solution or we can have infinitely many solutions. And the third case could be that we have no solution. So, but if there is a solution, we want to see if that is the only one, or in other words, is the solution unique? Now, this question about uniqueness and existence, this will keep bugging us throughout the course, throughout this semester, because almost every section, at least every chapter, we will see the question of, does the solution exist? Is it the only one, or do we have a unique solution? So, uniqueness and existence. So, be familiar with this question. Okay. So, now let us see another example, and maybe this will help us decide or come up with an idea of when the solution will exist, or when will it be unique, and when will it not be unique, or when will the solution not exist. So this is an example. So it says, determine if the following system is consistent. So this is the system of equations given, and now we create the augmented matrix by writing the first. We will write the coefficient matrix, which from the first row we see there is no x term. So it means the x term has a 0 coefficient. So we can add it like this. So now I picked the coefficient. So we have 0, 1, -4. So I put them in the first row. And then 2, -3, 2 in the second row. And the 5, -8, and 7 in the third row. And then on the right side, end of this matrix, we write our right side of the equations, 8, 1, 1. And then we will put a line, vertical line here, just separating the coefficient matrix from the this column matrix, 8, 1, 1. Now we want a 1 in the place of then over here, basically. So we don't want this to be a 0. Okay. So first thing, it could be anything. It could be any number but 0. Eventually we can convert it to 1 by just multiplying the row by whatever the number is, the reciprocal of that number. So what we can do is, because our other 2 rows have a non-zero number in the first column, so we could change the first row with any of the 2 rows. We could change the first row with the second row, or we can change the first row with the third row. So here we have changed or exchanged or interchanged the first and the second row. So this is how we will write R1. So it is important that you write these these kind of statements, so that the reader can see what you are doing, because otherwise it's so many things going on here that if you don't mention, then the reader will have to guess has been done, and it takes up a lot of time. And if you look at back your example, you won't understand what you did. So we are going to exchange or interchange R1 and R2. So we write R1. So remember, this is something I mentioned in the first video, that these rows are named. So this is row 1, this is row 2, and this is row 3. So we write here row 1, and then we put a double-sided arrow, row 2. So it means the row 1 has become row 2 and row 2 has become row 1. So what we do now, we have to eliminate this 5. Now we could do two things. We could make this 1, and how can we do that? Well, if we do, next our operation is 1/2 R1. If I do that, notice here what happens. So the first row becomes 1, -3 over 2, 2 over 2, which is 1, and then we have 1 over 2 in the end, the last column. But now what has happened, we see some these fractions in the first row, and now we will have to, when we add a multiple of the first row to second or third row, we will have to deal with the fractions, which is okay, because eventually at some place you have to deal with the fractions. But at this time we don't want to make that the fraction. So what we are going to do is just take this quantity 2 in the first. So what we do now, this is the process. The first thing you do is you keep the first entry of the first row, or we say the entry which exists in the intersection of the first row and first column. So we want this to be a non-zero number, which we have right now. Now we will use this number to make the entries below it 0. Now in the second row we already have a 0, so we don't have to do that operation. So it saves us one operation or one row operation. But now in the third row we have a non-zero entry. So I want to make this a 0. So what I do is I want to use the first row. So how can I use it? The only way we are allowed to use the row is that we multiply this row by some number. So we multiply the first row by some number such that when we add it to the third row, this quantity or the number over at this place becomes 0. So what does that mean? It means if I do this, I divide it by 1/2. I'm divided by 2 or multiply by 1/2 and then multiply by -5. So if I do that, this quantity, so I'm the first entry in the first row, if I multiply it by, in other words, by -5 halves, it will become -5, because I'm multiplying it by 2, the 2 by this quantity, so it becomes -5. And then when I add -5 to 5, it gives me a 0. So this is what we are going to do. And in the beginning, you may write these steps on a side, or on a separate paper, and then transfer them over here later on. But also, you will notice that as you move on, keep doing these, enough practice with these problems, you will can easily do these operations in your head. Okay, so what is the operation that we are doing? We are going to do this. So we write over here. So R1, we are going to multiply it with -5 over 2. So -5 over 2 R1, and then we are going to add it to the row 3. And what will happen, this will give us a new row 3. So this is what you need to remember. So although we are multiplying the R1 by -5 over 2, we are not going to change it. We will just copy down the row as it is from the top. So row 2, -3, 2, and then we have the augmented matrix. Okay, so now let's do the operation. So when I multiply the first row by this quantity, what am I getting? The first one I'm getting 5. In the second place, so we have -3, and we are going to multiply by -5 halves. And the 2 again is the same thing, and the 1 is easy. So I end up getting -5, 15/2, -5, and then -5 halves. And we are going to add this to 5, -8, 7, 1, which is the third row. So this is a side work, remember? And then we just add them. So let's add them. So first one is going to give me 0. Now I have 15/2 minus 16. What is that? So 15/2 minus 16, minus 8, which becomes 16/2. So we had, so in place of 8, we have now 16/2. So we end up getting -1 half. So that is what we will write in the place of second, place, or the quantity which comes in the third row and second column. So the next one is 2. So what are we getting? We have -5, and we are going to add it to, 7. So we are adding the -5 to 7, which will give us 2. So this gave us -1 half, next gives us 2, and the next one is -5 half plus 1. So this will give us -3 halves. So now you see the next matrix. We have the first row as the previous matrix. The second row is exactly as what we have in the previous matrix, but the third row is changed. Okay, and we got our goal, which was to have this, the entry over here equal to 0. The next entry, the next step in the algorithm is to have a non-zero element at this place. So notice here, this is called the diagonal of the matrix. So later on we will study square matrices. So a square matrix is a matrix which has the same number of rows and columns. So if you notice, the coefficient matrix is a square matrix, but our augmented matrix, of course, is not a square matrix. So we actually, that's why we would like to have this line in between. So we would actually like to have the non-zero entries over here, if possible. And we want all the entries below this. This is called the diagonal of the matrix, we want the entries below the diagonal 0. That is our first goal. And then later on we will make the entries above the diagonal 0 as well. But first job is to make the entries below the diagonal 0. So now we have this entry 0, we have this entry 0. Now our job is to get the entry over at this place 0. But it is not -8 at this moment. Now this entry is -1 half. Now notice we cannot use the first row to make this entry 0, because if I use that by thinking of this quantity, which means if I multiply the -3 by -1/6, -1/6. So if I multiply this by -1/6, I end up getting 1 half, and when I add 1 half to -1 half, I get a 0. But then what will happen? Well, you have to do this to the whole row, So we will have to multiply this by -1/6, 1/6 times 2, which gives us -1/3, and then I add it in here, I get a -1/3 over here, which is not what we don't want, because we just made it 0. We don't want to undo the thing that we did, okay? So we cannot use the first row now. So what do? Well, look at the second row. That is why we made it 0. That is why we made this quantity 0. So it's and sorry, this quantity 0. Well, this was already 0, but that's why we need it to be 0, because now we can use the second row to make the quantity in the third row and second column 0. So since we have a 1, which is the simplest number, so we just multiply the second row by 1/2 and add in the third row. So we write it like this: 1/2 times R2 plus R3 is going to give me new R3. So the first row we copy as it is, second row we copy as it is, because these two rows are not changing. Only third row is changing. So we multiply the second row by 1/2. Is it? Yeah. So what does it become? So it looks like 0, 1/2, -2, and 4. And now we are going to add the row 3, which is 0, -1/2, 2, and -3/2. So when we add them, so the 0 plus 0 is just 0. 1/2 minus 1/2 is 0. -2 plus 0 is 0. And now this thing, 4 minus 3/2. 4 minus 3/2 will be what? 8 over 2 minus 3 over 2. So it gives us 5 over 2. So I have 5 over 2 here. So now we have a 0 over here. In the previous example, you must have noticed that we didn't have a 0 here. We had a number here. So and we could easily we did. We used that number to create zeros on top of this quantity, or above the quantities above this number. We made them 0, and then we also made the quantity here 0, so that we could easily get our solution. But in this case, we cannot do that. So we have to stop. Now we cannot do any other row operation. We could, but well, the only thing that we could do now is make this quantity a 0, because we cannot do anything now at the bottom. So in order to make that quantity 0, so we want to make this quantity 0, the -3 over here. So what we can do is multiply the second row by 3 and add in the first row. So what I'm going to do next is I'm going to multiply the second row by 3. So I said 3 R2, and I'm going to add it in R1. So what does it look like? So it is going to be, the second row will look like 3, -12, 24. And the first row is, sorry, there was a 0 in the first place, which I forgot to write, and this is to be erased and then written again. So it is 0, 3, -12, and then 24. And then we are adding that. So we are adding the first row, 2, -3, 2, 1. So we get 2, we get 0, we get -10, and we get 25. Okay. So what has happened right now? Just the first row has changed. The second and the third row are going to stay as what they are. So the matrix that we get is actually, let me see if I can add a paper here, one page, so that it's easier to show you what is happening. Okay, so add a page. Okay, there you go. So we have now the new matrix is going to be, so the second and the third row are not going to change. So what I do is, I actually, before I do the step, this thing, I will write the rows which are not going to change exactly as what we have, and then do the calculations and write my third row, the other row which is going to change. So the new row now, first row now is 2, 0, negative 10, 25. Goes on that side of the line. Okay, now we read our the equations from the matrix, or we extract equations from the matrix. So remember how we created the matrix, and now we have to know how to go back to the equations from the matrix. So remember, this first column contains the coefficients of the variable x1, the second column contains the variable x2, and the third is the coefficients of variable x3. And these are the numbers which are going to be on the right side of the equality sign. So let's read them from the bottom. So if you look at the bottom line is saying that 0 is equal to 5. How does it say that? Well, because this will mean this is the coefficient of x1, so 0x1 plus 0x2 plus 0x3 is equal to 5 halves. But this all means 0, so we are getting 0 is equal to 5 halves. Now this is not true. Now we don't have to look at the other equation, the other two equations, because we saw that we are getting a untrue statement or a false statement. So this tells us that there is no solution to the system. So the system has no solution. Okay, so that is what we found. So what next? Now basically again, so it was the matrix didn't give us a solution. It means the actual system has no solution. Okay, so this is how you can see by doing those row operations. When we will have one solution, and we saw another example that when we have no solution, so we have still to see an example where we get infinitely many solutions, and that is going to come in the next section, 1.2. So now see you in 1.2.